Okay, we are going to go now to mechanics, chapter 9, which is actually the second chapter of mechanics. And this is constant acceleration, or the SUVAT formulae. And this is for me where it gets like proper mechanics. Last chapter wasn't really any calculations or anything. So this is where it really kind of starts. And we're going to begin by looking at velocity time graphs. Displacement time graphs are also in the specification. They don't really get asked about because there's so much in GCSE that we've got here. But we'll have a look at velocity time graphs in more detail. So again, this is just a revision video. I'm not going to be explaining a lot of things in much detail, just kind of giving you the facts. So we should remember that the acceleration is represented by the gradient of the line, that the displacement or distance traveled is represented by the area underneath the line, by the area under the line, I should write, so that we've got a little bit more proper grammar here. And if you are ever needing to find the area, it's a good idea to know the formula for the area of a trapezium, which is a half a plus b h. Sometimes people are just obsessed with splitting things up into triangles and rectangles, but usually those people make mistakes. So I would really recommend using the area of a trapezium. Now, if you do have a displacement time graph, the velocity is represented by the gradient of the line. And as you get to variable acceleration, that kind of should make a bit more sense. When you differentiate displacement, you get velocity. When you differentiate velocity, you get acceleration. And we know that differentiation is to do with gradient. Anyway, I'm getting a bit distracted because mechanics is my favorite kind of thing that we have in A-level maths. So we're going to dive straight in with this velocity time graph question. It says, a train travels along a straight horizontal track between two stations P and Q. In a model of the motion, the train starts from rest at P and moves with constant acceleration 0.3 meters per second squared for 30 seconds. The train then moves at constant velocity for 20 seconds, then moves with constant acceleration 0.1 meters per second squared for 15 seconds, before finally decelerating to come to a rest at Q. The distance between stations P and Q is 0.855 kilometers. Calculate the value of the train's constant velocity, find the maximum speed the train reaches, and sketch a velocity time graph for the motion between P and Q. Now, these first three parts, you might actually find it easier to start getting some information onto the diagram, and then we can use that to help us answer part 1 and part 2 that we've got here. So to get a bit of a sketch, we know that it's going to have some constant acceleration, 0.3 for 30 seconds. So constant acceleration starting from rest is just going to be a straight line with some kind of positive gradient, and that is just going to be for 30 seconds. We then know that it moves at constant velocity for 20 seconds. It just is a sketch, so it doesn't need to be perfectly proportioned and spread out. 20 seconds extra will take us to 50. It then has constant acceleration. That's a positive acceleration of 0.1. So it is going to have a positive gradient, but it's not going to be the same steepness. In fact, it's going to be a third of the steepness, and that's just for 15 seconds. Again, I'm just trying to get it like roughly correct on the diagram like this. 15 seconds takes us to 65. And then it says it finally decelerates to come to rest at Q. So I don't know how quickly it's going to decelerate. I don't know if it's going to be really steep, really shallow. You wouldn't get penalized if you drew it like this, or like this. It really, really doesn't matter. I'm just going to put it over here somewhere. And we don't know how long this sort of time is going to be at this last stage. So I've got the speed time graph drawn, but I think I actually need to look at part 1 and part 2. It says calculate the value of the train's constant velocity. So I need to know this part. Now you could use the SUVAT formulae for this, but I actually think we can just use a bit of intuition, right? It says that the acceleration is 0.3 meters per second squared for 30 seconds. That means that every single second it is increasing by 0.3. That's literally what the definition of acceleration is. It means that the speed is increasing by 0.3 every second. So all I need to do is 0.3 multiplied by 30, which I believe is just 9. Of course it is. 0.3 times 30 is just 9, meaning it just gets to, at this point over here, 9 meters per second. So our answer to part 1 of the question is just this. Now, if you did want to do it using SUVAT, you could have said that the velocity equals u plus at, which I'll discuss in the next video. U is 0, the acceleration is 0.3, and the time is 30, and we do still come up with that 9 that we've got there. Now, for part 2 of the question, it says find the maximum speed that the train reaches. So in this gap, for 15 seconds, it is accelerating at 0.1. So it's going to be 0.1 times by 15, which is 1.5, meaning it gains 1.5 meters per second in this bit. So that maximum speed that it will reach, even though that dotted line has gone a bit wonky, let's see if I can make that look a little bit better without disappearing, getting the whole thing to disappear. Let's go this way instead. So it's increased by 1.5, meaning that this is 10.5. Now that's just with the intuitive method. If you wanted to do it using this v equals u plus at, we could say that v is equal to u, which is 9, the previous speed, plus the acceleration multiplied by 15. And 9 plus 1.5 is 10.5. And so now we've actually done part 3, which is sketching the velocity time graph. We can't fill this value in that we have over here, but these key values are important to get the marks for this part 3 of the question. It then says find the total time it takes to travel between the stations. So for part 4 of the question, we know that the area is equal to the distance. And the distance is 0.855 kilometers, which we need to have in meters, which is going to be 855 meters. So the area is 855. So I'm going to say that 855 is equal to, now I'm going to try and do this as efficiently as possible. I could see it as a triangle and a rectangle, but I'm going to just see that as a trapezium. And for that trapezium, it is going to be a half. The A and B are going to be this part and this part. So the bottom of that is 50, and the top of that between 30 and 50 is 20. If it helps you, you can label things on your diagram like this. It might make you make fewer mistakes. And the height of that is just the gap from here to here, which is 9. And I'm just going to highlight that's in yellow to show you that that was what I calculated. I'm now going to find the area of this green part, and this is one I definitely want to do as a trapezium that we've got. So I'm going to do a half the A plus B. Well, it's this time it's this one and this one, which is the 9 and the 10.5. And I'm going to multiply that by the height, which is now this gap between 50 and 65, which is 15 that we have. And then our last part is the area of this triangle. Remember, a triangle is a half times by the base times by the height. Well, I'm just going to label that this base that we have here, let's just give that a label. I'm just going to call it capital T. So that's a half times by T times by the height of this triangle, which is 10.5. So I'm going to try and do this to solve what T is equal to, okay? I'm going to do 855 minus this. So 855 minus a half times by 50 plus 20 times by 9, minus a half of 9 plus 10.5 times by 15. And I've typed something in my calculator wrong. Let's put that in there. Okay, I'm typing so much in my calculator that's wrong. What have I typed? Okay, there we go. And that is equal to 393.75 with the subtracting. So 393.75 is equal to this a half times T times 10.5. So 10.5 times a half is 5.25. So that is 5.25 T. So my last step is to do that division. So it's 393.75 divided by 5.25, and I get that T is 75. So now I know on the diagram, this value here is 75 seconds. So I need to make sure I answer the question, which is to find the total time it takes to travel between the stations. So the total time, well, it took 65 seconds to get to here, and we're adding on another 75. So 75 plus 65 is 140 seconds, or 2 minutes and 20 seconds. But I'm pretty happy to give it like that. And then it says, hence find the deceleration of the train in the final section of its motion. Now, again, you could use SUVAT formula if you wanted to, but I'm just going to kind of use a bit of intuitive maths here. So it is at 10.5 and it takes 75 seconds to do that. We're just trying to say it's losing 10.5 meters per second to go from 10.5 to 0, and it does that in 75 seconds. How much is it decreasing by every second? Well, that would just simply be 10.5 divided by 75 to get how much is that per second. 10.5 divided by 75 is 0.14 meters per second squared. And because it's already asked for the deceleration, I can just write it as 0.14 meters per second squared. If it said, what is the acceleration, I would write negative 0.14 meters per second squared to show that it was a deceleration. And you can verify that if you use SUVAT methods for this, with u as 10.5 and v as 0 and t as 75, you'll still come up with this minus 0.14, indicating the fact that it's a deceleration. And then our last part, it says, suggest an improvement to the model to make it more realistic that we've got here. Well, we have got that it is going to just have like it's going to instantly go from acceleration to velocity, which is unlikely that we have here. It's more likely that there is going to be a smooth change between the different stages. So we could have a smooth change from acceleration to constant velocity. It's not realistic to have these kind of sharp points here. It's much more realistic, and I'm going to erase this afterwards, to have like a smooth part like this and then smooth here. The whole thing is much better if it's like a smooth kind of line. So we just need to kind of express that in the question as well. Okay, the next thing that we have a look at is the constant acceleration formulae, which most of the time, most of your teachers will probably call this the SUVAT formulae. But I like to say the constant acceleration formulae because you can only use them if the acceleration is constant. I'm not going to read through all of these, but these are in the formula book. I would expect my students to have these memorized. Each of these 5 equations has one of the 5 letters of SUVAT missing. Okay, so that's why there are 5 of them that we have. We're just going to dive straight in with this question. It says that a car passes a checkpoint at 9 kilometers per hour and then accelerates at a constant rate of 3.1 meters per second squared. Find the speed of the car in kilometers per hour after 6 seconds. So I think that we need to use our standard notation, or our standard units, which is going to be meters and seconds. So this 9 kilometers per hour, I want to do a quick conversion for this. Now, 9 kilometers per hour, I'm going to go and say that 9 kilometers per hour, this is the same thing as 9,000 meters per hour. So that was times in by 1,000. And I want to find out how far that is only going to be going in a minute. So this is going to be dividing it by 60. It's obviously going to go a 60th of that distance. So I'll do 9,000 divided by 60. So that's 150 meters per minute. And then to get that in per second, meters per second, I will divide by 60 again. I'm going to divide by 60 again, I get 2.5. So this is 2.5 meters per second. Now there's loads of different ways of doing that, but I kind of like to do it a stage at a time. But it's basically got to multiply by 1,000 and a divide by 60, a divide by 60, which is a divide by 3,600. So now I know that its initial speed in meters per second is 2.5. We know that it's accelerating at a constant rate of 3.1. And we want to find the speed in kilometers per hour after 6 seconds. Now, lots of people start off by writing SUVAT. I do not like doing that. I only like writing down the letters that I have, and then I like writing down the letter that I'm looking for, which is to find the final velocity of that car. And the reason I like to do this is because then I can see the 4 letters, and my brain naturally will go like, oh yeah, I know the formula that connects those. It's V equals U plus AT. Whereas if you still see an S there, your brain is getting a bit confused about what it's looking at. So I recommend only writing down the ones that you have. So V is equal to U plus A times T. So it's 2.5 plus 3.1 times by 6, which is 21.1. And then I'll just do the opposite of this process to get it back into kilometers per hour. So this is currently in meters per second. I'm going to multiply it by 60. I'll multiply it by 60. And I will divide it by 1,000. I've done the opposite, and the opposite. And I get 75.96 kilometers per hour. 75.96 kilometers per hour. But remember, in mechanics, you do need to give your answer to, have I got it somewhere else on here? No, I haven't got it on this slide. It's on my next one. You have to give it to 2 or 3 significant figures. So I'm just going to give it to 2 significant figures, which is 76 kilometers per hour to 2 significant figures. So that was part A of the question. Then part B is just trying to find out the distance that has been travelled in those 6 seconds, and we want it in meters. So I'm going to use the fact that U is 2.5, The acceleration is 3.1. It's traveling in those 6 seconds, and I want to find out what the displacement is. Now I can very clearly see the formula that connects those is the S equals ut plus a half at squared. So the distance is going to be 2.5 times by 6, that's u times t, plus a half times by the 3.1 times by the 6 squared. So it's 2.5 times by 6 plus a half times 3.1 times by 6 squared, and that is 70.8 meters. Don't have to do that any rounding. If you wanted to, you could say it's 71 meters to two significant figures, but that's perfectly fine like that. Now with vertical motion that we have here, when you do vertical motion, you should always choose a positive direction. It doesn't matter which. You can either do up is positive or down is positive, and indicating your positive direction can help reduce silly mistakes being made. Now acceleration is always vertically downwards, and typically we will use that g is 9.8 meters per second squared. Displacement is the distance between where it starts and ends for the journey that we are considering, and at the greatest height v is equal to 0. So let's have a look at this question. It says a small stone is projected vertically upwards with speed 12 meters per second from the point A, which is 8.4 meters vertically above horizontal ground. The stone hits the ground t seconds after projection. The stone is modelled as a particle moving freely under gravity. And we're going to do a few different things here. Now, I always like to start off with a diagram. So here is the point A, and the stone is being projected vertically upwards with speed 12 meters per second. We know it's then going to go up, and then it's going to come down and it's going to hit the floor over here. We've been told that this distance is 8.4 from here to here. And so I think we're pretty much ready to go. I might like to indicate that gravity is always going downwards with 9.8 like this. So we're going to start off by finding the speed with which the stone hits the ground. Now you can choose, do you want to do upwards as positive or downwards as positive? I'm actually going to show you them both and show that they work. Now if I say that upwards is positive, my value for u is 12 because it's going up. But my acceleration is going downwards, so it's minus 9.8. And if we're talking about its displacement, and we're literally just saying from the beginning to the end, I don't care that it goes up and then goes down. I'm saying, imagine it at the beginning, you took a photo. Imagine it at the end and you took a photo. From here to here, it has displaced downwards 8.4 meters. You heard me say downwards. Downwards means that it is going to be a negative. So it is negative 8.4. We're going to try and find out what v is equal to. Now in this particular case, I don't even know if it's going to matter if we do up and down, but we'll see, let's see. Now the formula that connects these is v squared equals u squared plus 2as. So subbing these things in, that is going to be 12 squared plus 2 times by negative 9.8 times by negative 8.4. So that is 12 squared plus 2 times negative 9.8 times negative 8.4. And we get that v squared is 308.64. So v is going to be the square root of this. Now, when you take the square root, we get to three significant figures, 17.6 meters per second. Now, you actually get the positive and the negative one. Now, given that this is our sort of upwards direction is positive, you should be thinking to yourself, actually, I was expecting a negative value for v, and that negative value is there because when you square root this, you'd get the plus or minus. But because it just says the speed, I don't need to say that it's a negative, but it would be a negative because it is going downwards. Now, I'm going to do this incredibly quickly. If downwards was the positive direction, well, u is up, so we would write it as negative. A is downwards, so it would be positive. S is downwards, so it would be positive. And we would find out what v is. We're still going to get that v squared is equal to u squared plus 2as. And when you put that in your calculator, I guarantee that gives you the 308.64. And when you square root it, I would take the positive for the 17.6 because it is going downwards, which is the positive direction. Okay, so it doesn't matter which one you do, you will come up with the correct answer that we have here. That was part A. We're now going to find the value of t, so how long it takes to do that entire journey from here to here. Now, sometimes people go, well, I need to work out the time from here to here, then I need to work out the time from here to here, then I need to work out the time from here to here. And most of the time, those are physics students. We do not do it like that in maths. It takes such a long time to do it that way. We can do it all with one formula. So I'm still going to use the same kind of values as before. I'm going to say that upwards is my positive direction. So U is 12, A is minus 9.8, the displacement is downwards 8.4 meters, and the amount of time it takes to get there is capital T. So the formula that connects these things together is S equals UT plus a half AT squared. S equals UT plus a half AT squared. So that is minus 8.4 equals 12 multiplied by T plus a half A. Well, a half of A is going to be minus 4.9 T squared. Okay, this is a quadratic. So if I put it all on one side, I get 4.9 T squared minus 12T minus 8.4 is equal to 0. And I can literally just put this, sorry for bashing around like that, just on the equation solver. So this is a polynomial with coefficients 4.9 minus 12 and minus 8.4. There's no method marks for this at all. One of those times is positive and one of them is negative. The positive one is 3.02, to three significant figures. The negative one is minus 0.568, but we'll reject that because it doesn't make sense to have a negative time there. Now again, if I was going to do downwards as the positive direction, we would get that U is minus 12, A is 9.8, S is 8.4, and very quickly you get an equivalent equation. You get that 8.4 is minus 12t plus 4.9t squared. If you do all of that rearranging, you get 4.9t squared minus 12t minus 8.4, which is exactly the same as this one, showing you that it doesn't matter which direction you take as positive, okay, as long as you're consistent throughout that part of the question. And you can flip midway through the question whether you really wanted to. And then for part C of the question, we are going to find the greatest height that the stone reaches above the ground. So I'm now interested in when it gets to this kind of top peak over here, which is where the speed at that point is 0. We talked about that in this little bit, okay? So I am probably going to take the upwards as my positive direction because I think the displacement will be positive and this initial speed is positive. So it kind of makes sense for me to do that. I'm going to do this in purple to show that we're talking about that ball. So going upwards here, the initial speed is 12. The final speed is 0. I want to find out the displacement. Oh, I also know that the acceleration is minus 9.8. And I want to find out what is that displacement. So UV, A and S, they are connected together by V squared equals U squared plus 2AS. So that is 0 squared equals 12 squared plus 2 times by minus 9.8 times by S. So that's 144 for the 12 squared. 2 times 9.8, negative 9.8 is negative 19.6. So 19.6 S is 144. And so S is 144 divided by 19.6, which is 7.3469 blah, blah, blah meters. Now that is telling us that it has traveled from here to here is 7.35 meters, but it wants the height that it reaches above the ground. So we need to add on an extra 8.4. So height above ground is going to be equal to the 7.346 plus 8.4. I'll round it to three significant figures, and we get 15.7 meters. And that is to three significant figures, which seems like a reasonable amount for it, okay? It wasn't like a kilometer or 800 meters or 200 meters. 15.7 kind of feels like a reasonable distance above the ground. So we will now have a look at a pretty challenging SUVAT kind of question where there are two particles moving freely under gravity, and not particularly helpful here. I've just said for two particles, carefully consider their journeys to set up simultaneous equations, a classic idea of there being simultaneous equations. So it says here that ball P is dropped from a point 50 meters above the ground. I'm immediately going to want to show this, like that P is going to be dropped from this point on this sort of cliff face or a building or something that is 50 meters above the ground. 1 second after P is dropped, another ball Q is thrown vertically upwards from the ground with speed 15 meters per second. So this is Q that we've got down here, and it's going upwards with speeds 15 meters per second. And for both of these, we're obviously going to have gravity acting downwards at 9.8. It says that the balls collide So at some point, these balls are going to crash together, okay? P is going to drop down like this, Q is getting shot up like this, and they are going to collide with each other. We want to find the distance above the ground where P and Q collide. So there's something quite useful here, or something quite important, is that P's displacement and Q's displacement should add up to 50. And also, we know something that Q was fired 1 second after P is dropped. So that means that P travels for 1 second longer than Q, or alternatively, we can say that Q is traveling for 1 second shorter than P, because it's leaving the ground 1 second later than when P is dropped. So we're going to try and set up some simultaneous equations. I will do P, and then I will do Q separately for this question, okay? So for P, it says it's just being dropped from up here. Now, if it's being dropped, that means that its initial speed is just 0, okay? So its initial speed is 0. I'm going to actually say that downwards is the positive direction. And the reason I want to do that is because then its displacement will be positive. And for Q, I'm going to say that its displacement is going to be positive for it being upwards. So you can see that you can use different directions within a question. So U is 0. The acceleration is downwards as 9.8. And we're going to say that it's traveling for t seconds. And we're going to find out its displacement. I'm going to call it S. I'll call it SP, okay, to show the displacement of P. And it's okay that I've got two unknowns here, because I'm about to do something for the second particle, which will also have two unknowns, and then I can do simultaneous equations. Now, this particle, I'm going to set upwards as the positive direction, because if I do that, then its displacement is positive, and I can simply say that the two displacements, which are both positive, must add up to 50. It's perfectly okay to do different directions within the same question. So for this particle, it is being projected with speed 15 upwards, so it's positive. The acceleration is negative. And then we talked about this just now, but the journey that Q takes to go from here to here, it was thrown vertically upwards 1 second after P was dropped. Now, people think, oh, I must do T plus 1. That is not true. This is how long Q is on the journey. If T is on the journey for T seconds, well, Q starts its journey 1 second later. So its journey is actually T minus 1. And then the displacement that we have for particle Q is just going to be SQ that we have here. Now I've got to this stage, I'm actually just going to start doing the simultaneous equations. Okay, I'll begin setting up the simultaneous equations. The things that's connecting these together is S equals UT plus a half AT squared. So that is S equals UT is just 0, and then I just have a half AT squared. So let me write this out. S equals UT plus a half AT squared. That part is 0. A half of A is 4.9, so I just get 4.9 T squared. And then for the second one, I'm also going to be using S equals UT plus a half AT squared. So that is SQ is equal to 15 multiplied by T minus 1. And then a half of the acceleration is now minus 4.9 times by T minus 1 squared. You can see why this is a much more complicated question. And then the final fact that we have is the displacement of P and the displacement of Q must be 50 when they add together, because that's how they're going to collide. They're going to be in the same place at the same time. That's why we're able to use this simultaneous equation here. So SP plus SQ is equal to 50. And now it's just a massive amount of maths. So SP is 4.9 T squared. SQ is 15 lots of T minus 1 minus 4.9 lots of T minus 1 squared. And that is equal to 50. Now, pardon me as I'm going to go through this quite quick. So it's 4.9 T squared plus 15T minus 15 minus 4.9 lots of, well, T minus 1 squared is T squared minus 2T plus 1, and that's equal to 50. So I am going fast. I do realize I'm going fast, but this has been a long video. So you get minus 4.9 T squared. You then get a plus 2 times 4.9 is 9.8 T, and then you get a minus 4.9 here, and that's equal to 50. This and this cancels, which is very convenient that we have. 15T plus 9.8T is 24.8T. So I have 24.8T. That's from this one and this one. I'm now going to do the 50 plus the 4.9 plus the 15. So that is 69.9. So that means that t, how long p is travelling for, is 69.9 divided by 24.8, which is not a particularly nice thing. As a fraction, it is 699 over 248. That is about 2.8 seconds, which again seems reasonable. But we need to find the distance above the ground where they collide. In other words, what is this distance? And we have an expression for that. We have that over here. So all I need to do now is actually find out what SQ is equal to. In other words, I'm going to take this expression for t that we have, and I'm literally just going to substitute it into those brackets. So I'm going to subtract 1 so that it's stored on my calculator, and I will just do 15 times by the answer minus 4.9 times by the answer squared, and we get 11.07. So I can say that they collide 11.1 meters above the ground. And that is to 3 significant figures. An incredibly challenging question for this, but I wanted to put it in there because this is the kind of thing that you might come across in the exam that we have, okay? So that is all of constant acceleration. I hope to see you in the next video, which is going to be about forces and motion. Thanks for sticking through this, guys. Well done.